Good morning, everyone. This is Payavala Bhavagna from Institute of Aeronautical Engineering IARE. Today, I am here to explain my complex engineering project of, course, EEE. And my concept is design and simulation of a basic LED blink circuit using multisim. Uh, I am from Computer Science and Engineering from Section A, and my roll number is 24951 A0559. Now, this is the project overview. It goes like abstract objectives, requirement, technology and methodology, block diagram, explanation, key diagrams and circuit diagrams, and merits and demerits, conclusion, and ends with a reference. Now let us dive into abstract. The design and simulation of electric circuits are essential steps in verifying and analyzing circuit behavior before physical implementation. This project focuses on the development of basic LED blink circuit using NI Multisim, a widely used simulation software in electronic engineering. This circuit employs fundamental components such as resistors, capacitors, transistors, and a timing device like the 555 timer in stable mode to achieve a continuous blinking effect of an LED. By simulating the design in multisim, the behavior of the circuit can be observed and optimized without the risks and costs associated with physical uh, prototyping. The study highlights in simplicity and efficiency of using multisim for educational and practical circuit design, demonstrating how simulation tools can aid in better troubleshooting design flows prior to a hardware implementation. Now let us know about few of the objectives. To design a basic LED blink circuit using fundamental electronic components, including resistors, capacitors, LEDs, and the 555 timer IC. The primary goal is to create a simple circuit that demonstrates the fundamental concepts of timing, pulse generation, and control of output devices like LEDs. To simulate the LED blink circuit using NI Multisim software, allowing for the validation and verification of the circuit's functionality in a virtual environment. This simulation process aims to ensure that the circuit operates as intended before any physical components are assembled. To understand the operations of the 555 timer IC in a stable mode and its application in generating a continuous pulse signal that drives the blinking of the LED. This objective includes examining how the 555 timer works as an oscillator and how its frequency can be adjusted based on external timing components, resistors and capacitors. To explore the effects of varying components values and the blinking frequency of LED, particularly by adjusting the resistor and capacitor values in the circuit. This objective aims to demonstrate how these changes affect the timing cycle and how one can fine-tune the circuit for different blinking rates. To enhance proficiency in using multisim for circuit designs and analysis, providing hands-on experience with a professional simulation tool. This includes learning how to troubleshoot circuits, perform virtual measurements, and optimize design for performance and accuracy. To analyze the impact of components tolerance on circuit behavior in the simulation environment, exploring how slight variations in resistors or capacitors values might affect the final performance of the LED blink circuit, and learning strategies of meditating such issues to evaluate the effectiveness of simulation in the design progress, highlighting the advantage of virtual testing in terms of cost reduction, time efficiency, and improved understanding of circuit behavior before building physical prototypes. To develop a comprehensive understanding of the importance of timing circuits, in electronic systems, providing a solid foundation for more complex projects that require precise control of time-based events. To document the entire process, including design steps, simulations, analysis, and results, in a clear and organized report that can serve as both an educational tool and reference for future circuit design and simulation. Requirements for a design and simulation of basic LED blink circuit using multism. Hardware requirements: computer system, a computer with sufficient processing power and memory to run simulation software like NI multism. Minimum specifications should include processor, Intel i5 or equivalent, RAM 8 GB or higher, storage 500 GB HDD or 256 GB SSD for storing project files and simulation data. NI multism software, a licensed copy of NI multism for circuit simulation. Multism is an electronic schematic capture and simulation program, allowing for the creation of circuit designs and performing tests virtually. Basic electronic components. If transitioning from simulation to physical hardware, the following components are required for building the actual circuit: 555 timer IC, resistors like example 10 ohms, 1K, etc. Capacitors, example 10 μF or 100 NF. LED, light emitting diode. Breadboard for assembling components if applicable. Connecting wires, power supplies, etc. Measuring instruments. If building physically, you need a multimeter to measure voltage, current, and resistance in the circuit. Oscilloscope optional. TC visualize the timing and frequency of the output signal. Software requirements. NI multism simulation software ensures that software is installed and licensed for use. It should include features such as circuit design tools, components libraries, 555 timer, resistance capacitors, LEDs, etc. Virtual oscilloscopes and multimeters for testing and analyzing the circuit. Simulation tools to run time domain and frequency domain tests. Simulation models for components. Pre-built models of the following components available in the multism library: 555 timer IC, resistors, capacitors, LEDs, power sources, etc. Now let us know about few of the knowledge and skill requirements. Basic electronic knowledge. You need a basic electronic knowledge, understanding of basic circuit components, resistors, capacitors, LEDs, and how they function. Familiarity with the 555 timer IC, specifically in astable multi-vibrator mode to generate pulses. Basic knowledge of circuit analysis. Basic knowledge of circuit analysis. Basic knowledge of circuit analysis techniques such as Ohm's law, current voltage relationships, and understanding of timings in circuits. Proficiency in NI multism. Knowledge of how to design, simulate, and troubleshoot circuits in multism. Ability to use simulation tools such as the virtual oscilloscope and multimeter for analyzing circuit behavior. Familiarity with the component placements, wiring, and setting simulation parameters in multism. Technology and methodology. Let's get to know about the technology and methodology used in this LED blink system. Technology. The project leverages NI multism, a powerful circuit simulator tool to design, simulate, and analyze the behavior of a LED blink circuit. Multism integrates graphical schematic capture, simulation, and analysis tools that allows engineers and students to develop and test electronic circuits without needing physical components. The following technologies and tools are integral to the project. NI multism simulation software. Multism is a circuit design and simulation platform widely used in electronics, education, and industry. It provides an initiative interface for designing electronic circuits and simulating their behavior in real time. The software features a vast library of components, including the 555 timer IC, resistor capacitors, etc., LEDs, etc., and advanced simulation capabilities to analyze voltage, current, and timing characteristics. It offers virtual measurement tools such as multimeters and oscilloscopes to observe circuit performances and simulation modes that allows for both time domain frequency domain analysis. 555 timer IC. The 555 timer IC is a versatile integrated circuit used in various timing applications, including pulse generation and signal oscillations. In this project, the 555 timer operates in ashtable mode, where it continuously switches between high and low states, thus generating a square wave signal that drives the LED blinking. Resistor, capacitors, and LED components. Resistors and capacitors are used to control the timing characteristics of circuit. By adjusting the values, these components, the frequency of the LED blinking can be modified. The LED light emitting diode acts as the output device, visibly indicating the periodic on-off behavior driving by the timing circuits. Virtual measurement instruments. The project uses virtual oscilloscopes and multimeters within Multism to measure and monitor the circuit's performance. These tools allow for real-time analysis of voltage, current, frequency, and waveform characteristics in the simulated circuit. Methodology. The methodology of the design and simulation of the basic LED circuit using Multism involves a step-by-step process as outlined below. Circuit design. Component selection. The first step in selecting the component necessary for the LED blink circuit. This includes the 555 timer IC, configured in ashtable mode, resistors, capacitors, and the LED. Circuit schematic creation. Using Multism, the components are placed on the virtual workplace. The 555 timer is connected to resistor and capacitors from the timing circuit. The LED is connected as the output device to visualize the blinking effect. Power supply. Power source such as 5 volts DC supply is added to the circuit to provide a necessary voltage and operations. Circuit simulation and techniques. Testing. Initial simulation. Once the circuit design is complete, the simulation is complete. The simulation is run within Multism. This allows the designers to verify the initial behavior of the circuit, ensuring that the LED blinks and the expected rate. Timing and frequency adjustment. By adjusting the values of the resistors and capacitors in the circuit, the blinking frequency of the LED is modified. The 555 timer's output pulse frequency is controlled based on the RC time constant, which determines the timing of the on-off states. Measurement and analysis. Multism virtual oscilloscope and multimeter tools are used to measure voltage levels, pulse frequency, and current through the LED. This data is analyzed to confirm whether the circuit behaves as expected. If necessary, design adjustments are made to optimize performance. Troubleshooting and optimizing. Identifying issues. In the simulation environment, any issues such as incorrect blinking rates or circuit instability are identified and corrected by inspecting the behavior of each component and adjusting components' values accordingly. Component turning. The resistor and capacitor values are adjusted iteratively to achieve the desired LED blink rate. The simulation tools help to visualize the impact of these changes in real time, allowing for faster optimization compared to physical prototyping. Documentation and reporting. Simulation results. The results of simulation, including voltage, current, and frequency reading, are recorded. Visualize snapshots of the circuit design, waveform outputs, and measurements are captured and compiled into a file report. Analysis and conclusion. A comprehensive analysis is conducted to assess the performance of the circuit, including any dependencies from the expected behavior and suggestions for improvements. Now let us look at the block diagram of this. DC power source, and after that timer, clock, then current limiting resistor, then LED, and then ground. Explanation. DC power source, typically a 5 volts or 9 volt battery or a DC supply in multism. Timer clock, often a 555 timer IC configured in an adjustable mode to produce the square wave on off pulses. Current emitting resistor protects the LED from excessive current. LED, light emitting diode that blinks on and off according to the timer pulses. Ground completes the circuit. Key diagram. Here we can look at the key diagram. Now it is something like this, and then another 2 LED flashing diagram which goes up like this. There is a DC power source, a lot of batteries, and it is connected to a ground at the end. Now let us get to know about few of the merits and demerits. Merits. Cost effective. Using multism for circuit simulation eliminates the need for physical components during the design phase, reducing material costs. The entire design process can be performed virtually, saving money on components, breadboards, and testing equipment. Time efficient. Simulation in multism allows for rapid testing and optimization for the circuit. Changing to the design can be made instantly, and simulations run in real time, speeding up to prototyping process compared to physical trial and error. Error free design. The simulation tool can identify design errors such as incorrect writing or component values, which can be difficult to detect in a physical setup. This prevents the need for debugging hardware circuits and allow for easier troubleshooting. Virtual testing measurements. Multism provides built-in virtual measurements tools such as oscilloscopes and multimeters, allowing you to monitor and measure key parameters, voltage, current, frequency of the circuit during simulation, providing immediate feedback and insights. Educating tool. The project serves as an excellent learning tool, especially for students and beginners. It helps in understanding the fundamental electronics concepts like oscillators, the role of 555 timer, and the timing behavior in simple circuits. Component optimization. The ability to adjust component values, resistors and capacitors, and observe real-time effects helps optimize the circuit. It aids in selecting the best values for achieving the desired performance, such as adjusting the blink rate of the LED. Safety. Now, since the simulation is conducted virtually, there is no risk of damaging components or electrical hazards, which is a concern with physical circuit assembly. It ensures a safer environment, especially for those unfamiliar with the hardware handling. Reusable design. The circuit design created in multism can be saved and reused for future projects or modified to suit different requirements without the need to start from the scratch. This promotes design reuse and efficiency in future work. Demerits. Limited real world interactions. Multism is virtual tool, and while it simulates most aspects of an electronic circuit, it may not perfectly replicate real world physical effects such as component tolerance, noise, and parasitic behavior, which could lead to discrepancies in actual circuit performances. Hardware constraints. Multism can only simulate idealized conditions. It cannot test the physical limits of real components. Issues like overheating, power losses, or electromagnetic interferences are not accurately reflected in the simulation. Learning curve. Although multism is designed as to be user friendly, beginners may face a learning curve when first interacting with the software. Understanding how to use all the features effectively, examples, simulation settings, measurement tools, may require time and experience. Software limitations. While multism is powerful, it may not support all types of advanced components or the most cutting edge technologies. Some complex behaviors might not be fully modeled or require more specialized software. Dependency on software. Relying solely on simulation software can create a false sensation of coincidence in the design. It's important to remember that real world circuits might behave differently due to environmental factors or components variations, which might not be fully captured in the simulation. Resource intensive. Running simulations with large or complex circuits can be resource intensive, requiring a computer with higher specifications. Lower end machines may experience slow simulation speeds or crashes during the intense testing, making the process less efficient. Cost of software. While there are educational versions, multism is a premium software, and purchasing a full license can be expensive. Some students, for hobbyists, may not have access to software without institutional support. Now let us get into the conclusion part. The design and simulation of a basic LED blink circuit using multism was successfully completed, achieving the desired amount of blinking LED controlled by 555 timer IC in astable mode. This simulation verified the circuit's functionality with the LED blinking at configurable intervals by adjusting resistor and capacitor values. Multism provided a cost-effective, time-effective environment for design and troubleshooting, offering real-time feedback through virtual measurement. Tools like the oscilloscopes and multimeter, the project reinforced fundamental electronic concepts and demonstrated the practicality of simulation tools for circuit design and optimization. Overall, the project was successful in the showcasing how multism can aid in both educational and real-world electronic circuit development. Now, this is the reference through which the design of multism of a basic LED blink circuit using multism was given by. Thank you.